Hello, this is the Tepid Coder here. Today I thought I'd have a little bit of fun. So, what I did was, I made a, air quotes, future-proof, and air quotes, library, just to show off how I might do that. Because I was thinking a lot about the DLL miniseries I was doing earlier, and what a perfect setup for a library might be. And I'm not saying this is the perfect setup, but this is what I came up with to make it as idiot-proof as possible. So the first thing is I'm leveraging the debug macro that I made in an earlier video. It was kind of an extension to that enum project that I did earlier, where I had the enum reflection macro. Anyway, I've made it so that there is a define you can use inside of this header called C++23 available. So if you define that, it'll be able to use the newest versions of it with standard print. If not, it's going to only define the C++20 debug printf version. I didn't include the C-like version where it's using fprintf. Could have done that. Maybe I could do it later. I don't know. But for now, this is what's happening inside the header. So I'll be using this function. Just wanted to share that real quick so people won't get confused later. So let's look at the actual library. So I call it feature proof library. .h is the header. Okay. The first thing I did in here to make it future-proof is I made it so that you have to define the version of the library you want when you're linking against it, including the header. And if you don't specify a version, it's going to complain. Now, what I'm doing with the version is the newer the version is, the more, let's say, features you can actually access in the API. So you might imagine there's new API functions being added. Maybe even there's functions being removed, but that wasn't the plan with this. I was thinking we'd just be adding new API functions and maybe changing the way they work. Maybe we're taking some structures or returning them, but the way the structure is changes each time. So this is going to basically allow more API functions to be exposed, the newer version you have, and it's going to determine the version of the structures that are used and exposed by the library that you get. So let's scroll down here a little bit. I did my own define for a bool, just because I wanted to have a 1-byte bool. I defined my own true and false to be an unsigned 8-bit integer value 1 and 0. These are just so the functions I define have intuitive arguments. That is to say, like if you have something that maybe you have like bool try something, you have like some values, A, B, C, and you're like, okay, here's like R for result. Maybe you're referencing it, right? It's not always clear what's going to happen. This is kind of an easy case, but maybe you have like these input arguments, is doing some calculation, and it's storing the result in R right there. This just lets you know that these are only inputs. They're not going to be modified. Because maybe I'm taking a couple of these by reference as well. Like this is a pointer to something. This is like that kind of a reference. It's not clear that I'm not going to be modifying this inside the function. But if I actually specify out right here, we know it's going to be modified by the function. So that's what these are for. It's just labels I made. They get replaced with nothing, so they're not doing anything functionally. They could be completely omitted, and it wouldn't do anything. In fact, they are omitted by the compiler. So anyway, this right here is a structure for internal library state. It's only used by the library itself, and is not really exposed in any meaningful way to the user. While they probably could do some kind of extern thing and grab these variables, they really shouldn't be. This is just explicitly internal library state. And as new things are added in new API versions, more stuff will just be dropped into here, realistically. Okay, now here's the interesting part. The API structure defines what endpoints are available to the end user. This initialization function is something they actually have to query from the DLL, but when they call it, it's going to fill, you can see as an output parameter, it's going to fill this API structure with all of the API functions that are available for that version. So you pass the size of the structure, since it might have a different size if you're using a different version of the API. There's going to be less functions exposed. So it's going to clear that structure out up to the size that you specify, and it's going to fill it with the functions from the specified version of the library. And that's it's going to return that way, and if it fails, it's going to return my TC false, which is just 0. If it succeeds, it's going to return my TC true, which is the unsigned 8-bit integer value 1. So that will evaluate to true. Okay, and I'm always going to expose an uninitialize function for the library. And then for version 1, we have a function called do something. Now, if you have a version greater than 1, this function is going to exist. If you have a version greater than that, greater than 2, more functions exist, right? Now, it's worth noting that the actual implementation of this function right here might change between versions. So even though it has to have the same return type and take the same arguments and have the same name, it can actually behave differently. So the function I point to when I call this might be something different inside of my API structure for version 2 than it is for version 1, and I'll show that. You can change the implementation without actually changing the function name between API versions and causing someone to break. So that's really nice. Someone doesn't have to do what you do in like SQLite 3, where there's like, I don't know, SQLite 3 connect v4 or something, right? It's like, well, if I use connect v4, can I also use like prepare v4? Maybe that doesn't exist. Maybe it's only like a prepare version 2 or something you have to use. You know, it gets confusing. You have to constantly go back to the documentation to make sure that you're using the right versions of things, and the versions you're using are compatible with other things, and like the numbers are inconsistent because maybe one function changed twice, the other one changed 10 different times between different versions. I'm not trying to pick on SQLite 3. It's a great library. I use it all the time. I love it. But that's just one way of solving the problem, right? The way I'm showing is a bit different. That's all. Anyway, I expose a new API function called do something else in version 2 of the library. Versions greater than 1, you can actually use it because it's going to persist in all subsequent versions of the library. Okay, the next thing I did, and this one doesn't necessarily have to be done this way, but what I did is I made it so that depending on the version of the library you use, it's going to have a different version of a structure that you're passing to and accepting from the library. What some people usually do is they'll just keep adding stuff at the bottom of the structure. If you add stuff on the top of the structure, it means the addresses of all the things that the library would expect or the consumer would expect will be changed. But if you add stuff to the bottom, that means there's just extra stuff at the bottom. So the addresses of these things that you can use are still correct. They're still valid. So that's one way to handle it without breaking the API. You could have an old version you compiled against, you're only expecting these, and if you link against a newer version of the library, and the stuff's down here, it doesn't matter, because you're calling a function that only modifies these anyway, so you won't have any issues. But if you use newer API functions, perhaps, it'll expect more of these arguments, and if you pass this old structure from the old header to it, then you're going to have issues, because it's overwriting memory past the structure that you passed the function you called. So the reason I did it this way is just because this keeps the structures smaller. There's no reason to have a structure that's intended for the newest version if you're only going to use an older version of the library anyway, right? You can target version 1, even though you're linking against version 7. Maybe there's 15 versions out there right now. So that should still be completely valid, and it's only going to use as much memory for the structure as it needs. Okay, so if we're in version 2, we'll have more stuff in the structure, right? So what I did for this here is I'm like pretending I'm making a server, right? We start out just making it as basic as possible. It's got a socket you can connect on, or a socket rather, that's used to listen for connections. Okay, you have the name of the server, you have the IP address of the server. It's just, you don't really need that, but it's just maybe debugging information you can dump. You have the local port you're hosting the server on. Okay, but maybe you had some issues with something like too many people making connections. And the first way you try to solve that is you're like, well, I need to make it so that I don't want to queue up more than 10 connections at a time, because it's really bogging my server down. And then I don't want to have more than 20 active connections or 100 active connections at a time, because past that point my server starts getting really bogged down and it's not really in use to anybody. And then maybe I want to make sure that people get timed out if they don't use my server service for anything useful after some period of time. So maybe they're just sitting there for 5 minutes keeping the connection open, pinging me, but all they're doing is pinging. Maybe I just want to drop that connection to make room for more clients, since I now have a max connection queue and a max connection limit for active connections. Okay, and maybe in version 3 that wasn't enough, so you decided I'm actually going to start blacklisting people from the server. Or, well, I guess that's a deprecated term now. I'm going to start filtering people out. Or maybe I'm going to make it so only specific people I want can connect to my server, right? Previously that was called like a whitelist. I'll call it an allow list, right? An allow list and a block list. Although block is kind of unintuitive, because you could be talking about a block of connections, like an AP block or something. You have the A, B, C, and D classes. So I don't know, maybe blocked list would be more intuitive in that case. Anyway, in any case, people know what I'm talking about either way. So in this case, what we have added now is like a list of IPv4 addresses that we want to either allow or disallow. Maybe that's what I should call it, like allow list or disallow list. I don't know. I'll have to think about it, and I'm going to keep forgetting because I'm so used to an environment where it was always black or white list or whatever, so it's just going to always pop out. It's not something that's going to be conscious when it happens. Anyway, yeah, we have a list of IP addresses we either want to filter in or filter out, and that's going to be determined by, allow or false, or not, allow it or not allow it. We're basically defining what this list does. Does it block or does it allow if it matches? So that's why I didn't call it like a blocked IPv4 list, rather. And that's why I didn't call this a allowed IPv4 list, because it could be either. Okay, and maybe you have like the number of IP addresses in here in this list. Now the mask is interesting because that means you can actually not only block out a specific IP address, but you can block out a range of IP addresses with the mask. So maybe you want to only allow connections on your local network. And if you do that, maybe you have something like a network that's like 192.168. 0 maybe it's 10. I've seen a lot of different numbers. Let's just say it's 15 or something. And then .x, it could be anything, right? So what you could do is you could mask these bits right here. So if all these bits match, then we don't care what this is. We're considering this a match. That'd be something like 0x ff 00, right? We don't care about the last chunk here. So you can put anything you want there. It'll still match. But this whole class right here has to match that 15. If I didn't put a whole ff here and I just made it the value 15, which would be 0f right there, that means it wouldn't match addresses like, actually, that is what you want probably, right? Yeah. No, it isn't. No. I'm second guessing myself. Anyway, that means it would only match the numbers that have these bits at the end. So if I had an address like 192.168.0. What's something that ends with an F at the end? It would have to be a multiple of 16 minus 1. Let's say I have like 32 plus 15. So that would be 47. So that number right there would match this, even though it's actually a different, a different IP class value for class C. Anyway, you're able to filter these things out. You want to filter it out using the entire class there for that mask to make sure it's exactly 15 and not some other extra crap like this. In the last class, we're not masking because you don't care. So if the mask matches when you mask the IP address and you mask this value with the mask, if those have the same value, then it's a match, right? And we can filter them in or filter them out. So yeah, that's kind of an idea there of how you might have structures that change between library versions and expose just the version of the structure that is associated with the specific version of the library that you requested when you linked against this header. Okay. And then anything else interesting? Yeah, down here I made it so there is a type def. I've shown type definitions for structures before. You can also do a type definition for just basic types, and this is a more complex type, but it's a function pointer type. And you can see right here the reason why I did it. You can initialize the variable with this type. This is actually a type here, which is a function which accepts an unsigned 64-bit integer, a size t, and a pointer to an API structure as its arguments, and it returns a tc bool type, which is really just an unsigned 8-bit integer that can be either 0 or 1. Okay, so I'm defining that as a type right here. I'm naming it the name of the function that's inside the library, and then I'm casting it with that type. And if I did it the manual way, I would actually define the type like this. There's the variable right here. It's called this, and its type is a function which takes these arguments and returns that value. And then I have to actually do that again to typecast and say it gets the procedure address from the DLL. And really, that's inaccurate right there. I should have like each module or something, or each library, let's say. But the point stands. Each library. Okay, so let's look at the actual code for the library. We'll show how this works out, right? Where you have different versions of the API functions. How I'm breaking that up inside the library. So this time I'm going to go to the CP file, and in here I have a list of little things that I wanted to cover when I was doing this. Make sure the library does those things. So inside the library I have some global state, and that was that structure you saw earlier. This isn't intended to be exposed to, it's not intended to be exposed to the, the consumer. However, it is in the header. It doesn't need to be. I could have just defined that inside here and hidden it, and maybe that's a better thing to do. But I could also have state specific to versions if I really wanted. I'm not really planning on doing that, but I could. Anyway, the way I'm breaking this up is all of the functions exposed by each version have their own namespace. So I can have the same function defined in multiple namespaces to get multiple implementations of the same function. And this also simplifies the process where I assign the function pointers. There's never going to be any do something v1, do something v2 for each version. It's just going to always be do something. It'll be the same in the structure, it'll be the same when I'm actually making the assignments. This makes the process a lot easier. So all this does is it prints the file line it came from, and it prints out, this is only a test with version 1, so you know what version you've gotten when you compile it. Okay, version 2, same thing for this function, it just says version 2 now. And it also adds a new function called do something else. Lets you know what version it came from, and it just says some garbage, doesn't really matter. Okay, but now we get to the actual part where we uninitialize and initialize the library. This is where I uninitialize. Now, I have to delete these output stream iterators, and I have to manually create a new instance of it during the initialization process, because when you load a DLL, any classes that are in global namespace are not guaranteed to be initialized automatically. So you need to make a function to initialize them yourself, and just assume that when the library is first loaded, that nothing is in a valid state until you call the initialization function. This uninitialization function essentially frees all the resources that is in that internal library state, and then it resets it back to a default state where you could call the initialization function again. So that's what's happening here. Now when you actually initialize the library, what it's going to do is it's going to say, okay, whatever the requested is a version, store that in our internal state in case we need it. We're going to try to create these output stream iterators for standard C out and standard C error. And then if that doesn't work, we're going to return false, and we're going to let the caller know that we couldn't allocate some resources that we needed. We're going to initialize all of the function pointers to 0 pointers. Pointers to null, right? It's not going to be a valid pointer. And the reason I'm doing this is for compile time checks later, where I can see if I didn't forget to, or did forget to, assign any of those function pointers to a function that exists for that version of the API. So I'll show that in a minute, but every version is going to have the initialization function and uninitialization function. And past that, we're going to have certain cases. Like, so for version 1 of the API, we're going to assign the do something function pointer to be the namespace version 1 version of this. If we're using version 2 of the library, we're going to use namespace version 2 version of the function, right? So we're getting the function for that version. And obviously, if this function hadn't changed, I could still just put ns version 1 in here, right? And this is not going to be any more confusing to the end user who's consuming our library, because they're not going to see any of this garbage where, like, version 13 uses version 6 still of some function, right? Either way, we just assign the functions as needed. Also, this one is adding the new function that's exposed in that version of the API. Okay, and by default, it returns false. We couldn't actually assign the functions you wanted because you requested an API version that's probably greater than the one that we have in the current library you're linking against. So you can assume maybe you have some super popular library, like maybe we've written something like SQLite 3 or like WinSock or like zlib, something that comes with a lot of computers by default. And maybe your program, the consumer application, requires version 10 of the library, but your user that's trying to run your program only has version 5. This will return false here because your user doesn't have a new version of the library that it needs. Okay. Now, if I've forgotten to assign any of the functions, like say I forgot to assign this, it's going to exist in the structure though, assuming I remember to put it there at least. So in that case, what's going to happen is I'm going to iterate through the structure, treating it like an array of function pointers, but I'm treating each function pointer, since they're all different types of function pointers, like they're functions to different types of functions, right? One might return void and accept void, the other one might return an int and take 2 ints or something. I'm treating them all just like a void pointer. I don't care what the type is, I just say it's a pointer. Where does it point? That's what this void means, really. It's a pointer to something, and it has some address. So it's a pointer to a void pointer. So really what I'm looking at is something like I have void pointer like this, but it's an array of those, right? So LPV array, right? Pointers. Maybe there's 10 of them or something, right? And I can access LPV array pointers, and I can look at the 0th element, be the first one. It would give me a void pointer. It's the first void pointer in a table. So it's just a table of pointers, and I can get whichever pointer out of that table I want, or array I want. I'm just calling it a table, whatever. Anyway, I'm going to iterate through that. And the way I know how many to iterate through is by looking at the position in memory of the first pointer, which is the top of the structure, up to the end being the number of pointers in the structure. Really, all that's in the structure is function pointers, which are just the same as regular pointers, the same size, rather. If it were a method pointer, it would be larger, but for a function pointer, it's the same size. So I'm able to do this. So it's the start address plus the size of the structure in bytes divided by the size of each element of the structure, which is each just a function pointer. So the size of a pointer. That gives me a number of elements. So if I add to the start of the structure the number of elements it has, it's pointing to the next index of a function pointer that doesn't yet exist. So it's the first function pointer that would exist after the last function pointer in the structure. So just to show that, imagine you have like one item in your array, right? Well, the bounds of an array is always like 0 to number of elements minus 1, right? So if I have one element, that element is at position 0. So element 1 is past the end of the array. So that's how the sentinel is working here, just to make that clear. It's probably really annoying for someone to hear that who already knows. Sorry about that, but so I'll make sure everyone can follow along. Anyway, I'm going to iterate through this array of pointers, one pointer at a time, and I'm going to say, hey, if it's invalid, if it's 0, you know, then it's a function we forgot to assign, right? We didn't assign this function pointer at this address, right? I don't know which function pointer it is. I could say which offset it is or something and say like the third function pointer wasn't defined. I could actually add that to it, but it doesn't really matter. Realistically, one or more API function references were not set for the requested API version. So keep in mind up here, I did this mem set, right? I cleared all of the structures bitwise by 0. So it's just all zeros, which means that all the pointers, when you evaluate them, are pointing to the address 0. Okay, and that's how I'm able to test like this, to see if any of these are 0. Okay, and if that didn't fail, that means that we're able to just return true, right? If we forgot to assign something, then we're not going to let the library be used, or I guess technically we are. The user could decide to use stuff anyway and just trust that what they need is available, but that would be ill-advised. Anyway, so return true in that case. We're able to assign everything I know about. So let's consider some things. If I'd forgotten to do this, but I defined it in the header, then it would be caught. Now, if I forgot to define it in the header and here, then, I mean, the user doesn't even know it exists, so that's hardly a problem, right? And if I forgot to actually make the function, well, that's not really forgetting something, it's just I didn't make the function, right? Maybe I forgot that I was going to make it and just didn't put it in, but this gives me a pretty good chance of doing everything right if I've actually written the function. So if I write the function, I might try to go down here and assign it, and then I'll forget to put it in a header or something. It's like, well, if I try that, it's not in the header, but it's something I'm trying to assign. It's going to complain at compile time when I build the library that it's not something I can assign because it doesn't exist in this API header, right? And if I defined it in the header and then forgot to actually define the function over here, and forgot to assign it over here, one or the other, it's going to catch me at, what do I say, at runtime when I use the library. So that's how that's working. Now at this point, let's look at the consumer application. This one will be a little bit less interesting, but what I did here is I made a class to wrap the loading of a DLL and its functions. All this does is call, load library A in its constructor. And this, I mean, you could replace that with like DL open for Unix systems with G++. And in its destructor, it calls free library, which would be DL close on the, Unix systems or whatever. And then it has one expose function to get the address of a function inside the loaded DLL. That's all that does. So it's just to scope the loading and freeing of the DLL. So here's the constructor loading it, here's the destructor freeing it. So that way if there's any errors in my project, it's automatically going to free it for me when the DLL variable goes out of scope. Now, I have a wrapper around the API itself called future-proof API, right? And I have an API structure in here, but I also have this DLL class in there as well. So when the destructor of this is called, it's automatically going to call the destructor of this once this destructor finishes. In general, the destructor happens in reverse order of the definition of the class members which have destructors. So if I define something else down here, let's call it something else, right? T, whatever it is, some type. This destructor is going to get called before this one. And it's kind of the same for constructors, but in reverse, right? It'll be the order you define them is the order the constructors are called, and then our constructor gets called last, because we might rely upon these being defined before we can actually satisfy our constructor. And yeah, if I have something else right here, the constructor for this might actually require this. So that's why that happens. And when I'm destructing, it's possible that I need to be able to access the class members before I finish destructing. That's why they have to destruct after we do. And that's actually the case here. I don't want to free the library until I call the uninitialized function from the API right here. So if this got called before our destructor, that would be bad, because I wouldn't actually be able to call the API structure function, which has uninitialized, because it would be in an invalid state if I freed the library. Anyway, not a whole lot going in here. I have a constructor which tries to load the library, and here's, you can see in our constructor we're loading the DLL file, and this can throw if it fails to load the library. If that throws, it's just going to not be caught by us, but by our caller. We're just going to propagate it back to them. Okay, so if we got here, it means we didn't throw, and we're going to try to find the initialization function in the library that we loaded, and then if we got an invalid function pointer from that attempt, we're just going to throw our own error, saying we couldn't load the function we needed. Otherwise, we're going to try to call the function, because we were able to do it. We got the function address. And then if this fails, because the library returns some kind of error, then we're going to complain about that as well with a throw. Okay, and when we destruct, all we have to do is call the uninitialized function from the library to clean it up. And here's our main function. I did the same trick I showed earlier, where I have a unique pointer to it, so that I don't have to worry about managing the lifetime of it by saying, like, you know, equals new whatever and delete when I'm done, right? This manages that for me. And I also wanted to be able to use a try-catch block without having to have all my code stuck in this try right here. So that's why I'm using a new operator internally within this unique pointer. I could have just, you know, made it like this, right? If I go in here, I could have put the entire body of the main function inside of here and said something like, I call it future proof API, call it FAPI or something, right? I could have done that, and I could have just done all my code in here. But then everything's, you know, this far away from the wall. I don't like that. It annoys me. So I'm dynamically allocating it and then using the unique pointer to free it up for me. Okay, and then I actually access the API functions using a const reference to an API structure that I'm pulling from my future API class. Now what I could have done is I could have made a bunch of pass-through functions that expose all of the exact same functionality for the version of the future API library that I'm linking against. But that's really tedious. Essentially, you can imagine I have this, you know, struct API, right? And here we have like function 1, we have function 2, ... right? You can imagine there's 50 functions in there. So inside my class, right, my future proof API, whatever. Future proof API. Anyway, inside of here, I'd have to make methods for all those functions, right? So function 1, you know, it takes some arguments, it has some return type. Oops. I'd have to say, you know, return API.function1, and then I'd have to pass those arguments in, right? And I'd have to do it for all those functions, just basically duplicating all that logic just to make pass-throughs. So instead what I did is I just made it so I can get the API function like this. I return it. So API, it's void, doesn't take any arguments, it's const, it's no except, because I'm just returning a reference to a function, or a structure that already exists. And I'm passing it, or returning it rather, as a const reference. That way they can't mess with the function pointers. There's no reason for them to be doing that. And they can still call the functions. That's just fine. So that's why I did it that way. I could be a bit more verbose and actually do a bunch of pass-throughs like that, but that's a bit silly, I think. This already works like a class anyway, in the sense that, like, you can do API dot whatever. It's got good encapsulation. I think it's perfectly fine. So I'm calling do something from version 1, and I'm also calling version 2's do something else. And this exists in both version 1 and version 2, but there's a different implementation for version 2, as you saw. So after all of that rambling, let's try and actually build a thing here. So I'll run it again. Okay, you can see it builds. I'm doing consumer, and you can see it's using version 2 of both these functions. So let's try a couple things here. First off, I want to try using version 1 of the library. you can see that I'm compiling the library with the newest version of itself, right? That's because if I didn't, it wouldn't have access to the newest structure members that it needs to be able to compile the code for the newer versions of the library, right? Some of those cases we have the newer versions have to assign different function pointers in the structure. So it's always going to be the newest version of the library here. Now, when you link against it, you can choose which version of the library you want. So you get that version of the API, the version of the structures for that API, and so on and so forth. So I'm going to actually use version 1 of the API now, and it's going to complain at me because I'm trying to use a function that doesn't exist in that version of the API. So here we go. You're going to say, look at this. Has no member named do something else. It literally does not even exist inside of the structure. And I'll just return to that structure real quick so you can take a look at it real quick. So inside of my API structure right here, if the version is greater than 1, it's going to define this function pointer. Otherwise, it doesn't exist even. So that's kind of great. It means the structure we got is actually smaller. It only includes the things we can really use from the library. And if we had any structures like this, we'd be using version 1 version of the structure, specific to that version. So the structures aren't even larger than they need to be as the API grows. Okay, so what we can do here is we can say, let's go back to consumer. Let's actually comment out that bad line. We're using something from the wrong version. Okay, and we'll build it again. Now it should be happy. Consumer. And you're going to see we're also using version 1 of the library. So to the consumer, I mean, look at the code. It's not really different at all. I just basically, in my compiler flags, said what version I wanted. I don't have to do it here. I mean, I could define this inside the project, right? So before I include this header, as long as I define it right here, say it equals 1, that's also perfectly valid. Or I can say it equals 2 here, as long as it's before I include the header, because that's going to determine what structures members exist, what versions of the structures and what members of the API structure itself exist. So anyway, that's all you have to do. Like, that's super easy for the consumer to use your library. I want to do one other thing here too. Let's look at what happens if I forget to assign something. Just so you can see that. Okay, so let's go over to the future-proof API.cp, and I'm going to intentionally, forget with air quotes to assign some function pointer for version 2 of the API. Okay, just to show that that works. So let's clear this. Let's build again. So if I run it, you can see right here, internal library error. One or more API function references were not set for requested API version 2. So you can see it actually caught that. But it's at the time you try to use the library that's going to catch that. Trying to think here. Anything else I need to think about here? So it will catch that. And at least at that point, you should have some kind of test you do, like integration test or unit test, what do you want to say, where when you build your library, you run your tests to make sure that all the functions you can call from your library are working. And as long as you do that, you're going to catch that error, right? And if you didn't, I mean, the consumer of your library is going to see this internal library error, and they're going to report it to you. So that's still going to be helpful. Anything else interesting about this? I think that's pretty much it. I have rules at the top here. I'll just go over those briefly before I end the video. So these are things I was just kind of like keeping in mind when I was building this to try and make it as future-proof as possible. So all exposed API functions should be versioned by sticking them in their own namespaces. So you can see I did that. That way I can have the same function name across different versions and easily assign them to the API structure. Okay, the API functions must be returned by a structure that is filled with function references to functions from specific versions of the API. I did that specifically, like I said earlier, to avoid having issues where I have like do something v1 and then do something v2 and then ... right? And maybe I have something else, like maybe I have another function called foo, which depends on the results of do something, right? And maybe it needs the results of do something v2. This wasn't defined until API version 2, right? That gets really confusing when you have that kind of thing. So this avoids that problem. You're just using functions from that version, which has the same name as always. So it should be a seamless upgrade for your clients. Okay, so any functions newer than what would exist in the requested API must be inaccessible. So I showed you that. If you compile for an older version, they simply don't even exist in the structure as function pointers. Okay, any structures used by the API must be passed and returned by reference. So that I didn't actually show, but that is just something helpful because if someone has a newer version of the structure, they're going to have more stuff in it. And if they try to pass us too much data, I'm not exactly sure what the implications of that would be when you copy more data than is used by the function. I think it would just be extra garbage on the stack that gets cleaned up, and it wouldn't really matter if they have a newer version than you. If they have an older version than you and they're passing up by copy, you're going to be reading from, uninitialized memory, really. You're not pushing that stuff on the stack, so it's going to be just garbage data in the stack you're reading to put into structure for the newer version of the API with an older consumer. So that would be bad. Anyway, I'm also kind of fixing that issue by having versioned structures themselves. Structures have the same name and everything, but depending on the version of the library linking against, you're getting a different version of each of the structures. Okay, so structure members may not be reordered. That's important because the offset will change between API versions. Thanks for that, Windows Security. Anyway, yeah, what was I saying? Structure members may not be reordered so that the offsets stay consistent between library versions. New structure members must be added after the current last member. You could rename stuff and it wouldn't be an API break, but reordering is a problem and adding stuff to the top of the structure is a problem. Okay, so the header for the library must require a compile time defined to specify the API version that will be requested so that only members of structures that existed for a given version library will be included. So I've gone over that ad nauseum at this point. All unused API functions references in the structure will be initialized to 0. That's just so I have that runtime check that I just showed a second ago, where it'll say there's an internal library error where it couldn't actually use all the functions needed, or you can't use all the functions you need, perhaps, because they're not all being assigned inside of the structure function references by the library at runtime during the initialization function call. That was an mouthful. Okay, anyway. Only return primitive types from the DLL, or types that are defined and controlled by the DLL. This one I didn't really show, but I would never return something like a standard string, or if this has a common dependency that your library might have as well, I don't return anything like that. I'm only going to use types, and work with types that I accept, and return types that I control, that I define myself and build myself. And it could be that internally I'm using something like a standard string, right? It's just that I'm not going to return a standard string. I'm going to return some kind of like constant character string or something, or maybe like a structure that has some kind of a, I don't know, a string pointer, like const char string pointer, and also like a free function. Although if it's const, I don't know if you can free that. You might have to typecast that. Either way, if I did that, I'd also provide some kind of allocator functions and deallocator functions for whatever objects I'm returning from the library. So that's also being defined right here as a rule. Pair any memory allocation functions with memory deallocation functions in the DLL, which are exposed to the consumer. And that's because you might have a different version of the like C runtime DLL inside of your application on Windows, for example. Like I could have compiled my library with an old version of Microsoft Visual Studio, which uses an older version of the Microsoft Visual C runtime DLL than the one that's in your process. You're going to have two versions of the Microsoft Visual C runtime inside of your address space. And when you free the library, it's not going to exist anymore. And if you try to call any allocation, deallocation function, it's going to be undefined behavior. If you try to mix your free function with my free function, that's also undefined behavior, same with realloc. So that rule's here, but it's not really shown. So if I ever expand upon this video, which, like I said, the whole thing just for fun anyway, I'll probably fill in some of these things and show them that I didn't actually show in this library. But for now, I think this is a pretty good starting point. I would love to see what kind of comments you guys have on this, and like what solutions you guys would, invent, and what you've actually done in the wild. Because typically, I mean, just typically, in reality, I haven't seen anything where people have gone through these kinds of lengths for a library to make it future-proof as possible and version-specific as possible. I haven't seen people do a lot of these checks. And a lot of libraries run into problems because they don't plan for these things ahead. So, yeah, if there's anything that you do at your company or for your own projects to make your libraries more future-proof and maintainable, debuggable, I would really love to hear what you do, because there's, I'm sure, tons of ideas that you guys have and things that you've done at work even that I haven't thought about that would be great things to implement. So I'd love to have a discussion on that. In general, I'd love to have more discussion with you guys. And if you find this video helpful and you liked it, please like, comment, and subscribe. And have a great day, guys.